Hey everybody, Sci-Fi Fish here, and today's topic, lesson 1 in our series we're going to be doing on what is science and what isn't science, is called Got Science. When is science not science fiction? And I think you probably all imagine that there's a clear delineation between those two, and that science fiction never, ever is passed off as science. But actually, it is every day. Science fiction is peddled as science all the time. And so how can we tell? How do we know what is science and what isn't science? Is there a way? Is it possible to know? And the answer, thankfully, is yes, there is. And I want to provide all of my viewers out there with the foundation for discerning scientific truth so that you can be a watchdog yourself on what scientists are saying or the scientific community is saying about anything. Okay? Because science has a very clear definition, but it's one that's been muddled beyond belief by the scientific community, so that they can say outrageous things and get away with calling it science. Okay? That's a clear distinction. Science is not the scientific community. The scientific community is just a group of people who happen to be scientists, and they all have flaws. They all have ideologies and agendas and beliefs, and they're all out there doing their own thing. And they're being paid money by this group or that group to do science on this or that, but their conclusions and what they come to may not be science at all. Okay, so there's a big difference between science and the scientific community. So I hope to explain that in this video. So what is science? Well, simply put, science is the scientific method. And the scientific method is a roadmap. It's a pathway to understanding, growing in knowledge about a particular thing or particular things. And so for anything to be considered science, it has to pass through all of the steps of the scientific method's rigorous test. And only then can it stand on that foundation. Okay? So what is the scientific method? Well, it's observe, hypothesize, test, and then becomes a theory. Okay, that's kind of condensed. If you go out and you look for definitions on the scientific method, you'll get a whole range of different ways they set that up. But if you boil it down and you look at it, that's what it is. Observe, hypothesize, test, theory. And we're going to get into that. I hope you're not all glazing over right now like, oh, good grief. Am I supposed to remember all this? We're going to get into each topic, each element, each step of the scientific method here in a second. Scientific method is incredibly simple. It's very common sense stuff. It's what we use every single day of our lives. We may not use every step of the scientific method. In fact, almost none of us plays it all the way out. But we're all, in our lives, we're all enacting at least the first and second step of the scientific method. All right. So I want to use an example. We're going to use an example, a simple everyday example to explain the scientific method. So let's say you're out mowing your lawn, and after about an hour, your mower quits. It stops on you. Congratulations. You've just performed the first step of the scientific method, which is observation. You've observed something. Your mower quit. So step 1, observe. And this is primarily the human senses. It's related to the material and the physical world. So it's seeing, hearing, smelling, tasting, touching, feeling. It's purely related to the physical world in most cases. So in this case, probably more than one of your human senses observed the mower stop, right? You heard it. Maybe you saw it, you felt it die when you were holding on to the mower, all right? So you've made an observation. And we make observations all the time, every day, that we don't do anything with, right? We ignore them all the time without going to the next step. I'm getting ahead of myself here, but going to the next step, which is forming a hypothesis, an idea about why that happened, okay? There are tons of things we observe all the day that we don't think any more about. You might see something and you just, you hardly even notice it, right? You see it, you observe it, but you don't think about it anymore. So you're stuck at that first step of observation. You observed something. But in our example, you probably want to know why your mower stopped, right? I mean, you got to mow your lawn. So it's important enough for you to think about, and that's crucial to the next step of the scientific method. So you start coming up with ideas, and that's what hypotheses are. They're just ideas, nothing more. So let's move on. You've made an observation, your mower died, now you're moving on to the next step, forming a hypothesis. So you start coming up with ideas that would explain what caused your observation. Hypotheses are trying to answer the question, why? And they're ideas, right? Ideas are great. Most of us generate ideas when we observe something. Who ate the last of the spaghetti, maybe, right? You open your refrigerator, the spaghetti's gone. That's an observation. And then you form a hypothesis. It must have been Josh, because he went to work and he probably took it for lunch, right? So that's a hypothesis. You came up with an idea to explain why the spaghetti's gone, right? Or maybe you order your coffee at the coffee store and you take a drink and it tastes funny. That's an observation, right? You form a hypothesis. You could form 100 different hypotheses, but maybe your hypothesis is, they must have done something different this time to my coffee. Well, that's an idea. That's an idea that might explain why it tastes funny. Maybe they put an extra shot of espresso in here. Maybe that's why it tastes different. That's a hypothesis, an idea. So in our example of the mystery of the lawnmower that quit, here are some hypotheses that could explain why it stopped working. Okay? A, a cloaked alien UFO must be hovering over you and it shut the engine off. Okay, it's possible. B, maybe I ran over a piece of rope or a string or something and it's hung the blade up and it cut the engine out. It's possible. C, a directed electromagnetic pulse from a secret orbiting satellite shut off my lawnmower. It's possible. D, maybe my lawnmower is out of gas. That's also possible. So there are 4 hypotheses, 4 ideas that might possibly explain why the lawnmower stopped working. Okay? A lot of us stay right here because it's work to take the next step, getting ahead of myself, which is to test your hypotheses. So a lot of us stay here, right? But that's not science. You haven't passed through all of the hoops, all of the steps. Because you just have a whole bunch of ideas and no idea if they're really responsible or not for what you observed. So some of us do stop here. Well, we don't, but if you did stop here, what would you do? You'd walk in the house and you'd say, well, Mom, or well, honey, too bad. The mower stopped and there's a whole bunch of ideas about how it might have stopped. It's probably a cloaked alien UFO over my head. But I don't know, so I guess I'm just not going to mow right now. What's your mom or your wife or your husband or your dad going to say to that? Are they going to go, oh, okay. No, they're going to say, why don't you go out there and figure it out? See, if you stay in the hypothesis stage, it's fun because you don't actually have to prove anything. You don't have to do any work. But you can talk all you want about what might have happened, what probably happened. But see, in this instance, you need to mow the lawn. It's a problem, right? So you're going to spend the energy to try to figure it out, to test your ideas, to see if there's any truth to any of them, or maybe you need to come up with more and add more hypotheses. Okay, so let's move on to the next step. Test your hypothesis, step 3. This is probably the hardest step of all of the steps of the scientific method, because you need to see if you can even test your hypotheses, right? That's important. And what you'll find out really quickly, is quite a few of your hypotheses are actually untestable. So if a hypothesis is untestable, it still is a really cool idea, but it's nothing more. It's a really neat idea, but that's it. Ideas are great, but they aren't very useful. I mean, you can't call them facts. You can't call them, this is truth, people. This is what happened. You can't say that about an untestable hypothesis. So we're only interested in testable hypotheses because that's useful to us. In this scenario, only things that can be testable are useful. So every day in our lives, though, we settle for untested hypotheses, untestable hypotheses maybe, with the observations that we see in our lives. You know, maybe you heard a noise, bang, on the window downstairs, and you go, "Hey, honey, what was that noise?" She says, "I don't know, maybe a bird hit a window." That's a hypothesis, that's an idea, but can you prove it? If you can't prove it, well, you know, you can't prove that a bird hit your window, but we oftentimes just stop it then go, yeah, probably. That probably was what happened, right? Or maybe you take a drink of your soda and you're like, man, this tastes different. This tastes funny. And someone could say, yeah, they probably didn't refrigerate it. It probably, you know, or maybe they changed the formula of the soda or something, right? And you go, oh, yeah, maybe. Okay, so we oftentimes in our lives settle for untestable hypotheses, but this isn't science, and it's not useful because it doesn't actually get to an answer. All right, it's just an idea. So in hundreds of ways, every day, we settle on untested ideas to explain away what we either can't test or don't want to spend the time trying to figure out. But for inquisitive people or people who actually have something to do, a job, like mowing your lawn, you need to figure it out. So you have to move forward. So let's go ahead and test our 4 hypotheses. Do you remember the first one? A cloaked alien ship is preventing your lawnmower from working. Hey, it's possible. Could be. But how do you test that? How do you test that hypothesis? You know, maybe someone in the world could come up with a way to test that. But I don't know how. You don't know how. I don't have a clue. So it doesn't help us. It's an idea that we can't test. So we set it aside and move on. We haven't eliminated it. We can't throw that idea away. We set it aside because we can't test it. So we just set it aside. Maybe we'll come back to it in the future. But this doesn't help us. It's not progress because we haven't eliminated any options. That could be true, right? Maybe someday someone will be able to come up with a test for that hypothesis, but not today. Okay, so we move on. B, maybe I ran over something with my mower, like a string or a rope or something, and it got caught in the blades and it caused the engine to stall. Well, hey, that's possible. But can you test that? Can you test that hypothesis? Actually, I can. I can flip the mower on its side, and I can take a look. So we do that. We flip it on its side, and we take a look down there, and we look at the blades, but there's nothing. The blades are clear. All right. We've tested that very good hypothesis, very probable hypothesis, and we found it to be wrong. It does not explain why the lawnmower stopped working. So we throw that hypothesis away. We don't set it aside. We throw it away because we disproved it. We proved it doesn't have anything to do with our observation. Okay, this is progress, not like the UFO hypothesis. This is progress because we've actually eliminated it from being a possibility. We can't do anything about that UFO idea, but we can do something about this. Okay, so we move on. Hypothesis C. Maybe a secret DoD satellite nuked my engine with a EMP pulse. It's possible. Can I test it? Maybe someone out there can, but I can't. You can't. So we're stuck again with an untestable hypothesis. So we have to set this one aside and move on. And it didn't help us at all. All right, D. Maybe I ran out of gas. Maybe that's why the mower stopped working. It's possible. Can I test it? Yes, I can. I can open up the gas cap. I can look inside. And hey, look at that. It looks empty. I get some gas. I pour it inside the tank. Crank it over and it starts right up. Well, hey, this hypothesis would seem to be the answer, right? Are we there yet? Have we arrived? Have we proven this scientifically, that gas was what caused the mower to not work, not having enough gas? In our normal, suburban life, we've arrived because we just fill it up, start it up, and go on with mowing the lawn, right? But not from the scientific method. The scientific method is so rigorous that there's another couple steps. So let's move on. So we've got our mower working again by adding gas. Now, step 4, lots of retesting. Lots of testing and retesting of your successful hypothesis. Okay, so after filling your mower up, now you're going to mow for another hour and see if it quits again. And in this case, it does. So that supports your hypothesis, right? Congratulations. But are you done? Not by a long shot. You have to do the same thing like 100 times more. And you get your friends and your family in on it. And you get them to test your hypothesis. You put an ad in the paper and you challenge the whole world to come and prove your hypothesis wrong. That the reason your lawnmower quit was because it ran out of gas. You challenge them. Come up with a better hypothesis than mine to explain what happened. I invite you. I challenge you. I want you to prove me wrong. Now everyone in the world gets to take a shot at proving you wrong. Who wants that, right? Who wants to be proven wrong, right? But this is the scientific method. It welcomes attacks. It welcomes disapproval because it's not interested in defending an idea. It's interested in the truth. It's interested in getting at the actual thing that caused the mower to stop. And it wants to be very thorough about it. It wants to know how to try to establish it as firmly as possible. Okay? It doesn't care about feelings or someone's ideas or their beliefs or their faith. It doesn't care for any of that. It only cares for evidence. Okay, so a hypothesis can have hordes of evidence supporting it, but if the hypothesis can't be tested, it can't move on from that idea. That's just an aside. That's another important thing to remember. Okay, so let's say your hypothesis that the gas tank was empty, that's what caused your mower to stop working. That hypothesis survives everyone's attempt in the whole world over like a year, 2 years, 3 years to disprove it. It survived all of their attempts to disprove it. Now we can move on. Only after all of the skeptics have agreed can we move on. Hey everybody, AmendaFish here. Just got to add some things that Sci-Fi Fish forgot to mention in his podcast on the scientific method. And that is that throughout the scientific method, the whole process, assumptions and presuppositions play an integral part in every step of the scientific method, particularly in the hypothesis and testing stage of the scientific method. So what does that mean exactly? Well, it means that you make assumptions as to what hypotheses seem reasonable. Which ones you go, that's stupid, I'm not even going to look at that. Or this one's a really good hypothesis to explain that observation. Okay, that's an assumption. You assumed that. You might have some evidence to support that, but you still have to make an assumption. So you make the best possible assumptions you can with the knowledge that you have. Now, some scientists, though, may not be making the best possible assumptions that they can. Maybe they're just bad at their job. Maybe they have an agenda. Who knows? Regardless, you make these assumptions You make and you have presuppositions before you come to things about what is reasonable and what isn't. So assumptions are integral in deciding which hypotheses make sense, which ones you're going to pursue, and which ones don't. Okay? Now, in the testing stage, you can make assumptions about this test that you did to disprove that hypothesis. Maybe you assumed that test was a good test of that hypothesis, but maybe it's not a good test. Maybe there's a better test to test that hypothesis that you're not thinking of. All right, but you assumed that was the best that you could do, or that was the best thing. So that's what you started with. And maybe it's completely wrong. Maybe that assumption that you had about that test to test that hypothesis with, maybe there's a way better test out there that would have shown that that hypothesis actually makes perfect sense. So throughout the scientific method, assumptions and presuppositions enter into it. And there's nothing wrong with that on the outset if you acknowledge that. If you understand this process, it's perfectly fine. But the minute that you start saying, well, this is the only thing, this is the only way, and there's no option for another opinion or another approach to this, that's a problem. So good scientists acknowledge their assumptions and they say, well, yeah, we made assumptions in choosing our hypothesis to explain the observation, and we had assumptions and presuppositions in our test, how we test. We tried to do the best that we could to weed those out so that we were as bipartisan as possible, unbiased as possible, but we acknowledge that we had to make some assumptions, but that we think they're the best assumptions that we can make right now. And then you leave it to the rest of the community that's going to test your theory when you're done with this and look at test your hypothesis and look at this all around the world, that they will come to an agreement. Or maybe they'll say, no, your assumption here's wrong. Your assumption's bad. Here's a better assumption. You need to start over. And that happens in science too throughout this process. So I just wanted to get this in here because Sci-Fi Fish forgot to mention how assumptions and presuppositions are influential throughout the entire scientific method and its process. And that'll come into play later when we discuss things like evolution, climate science, the age of the Earth, the origin of the universe, all that stuff. We're going to get to all of these things. We have to set the foundation first, which is what, we're trying to do here if he would just let us do our job. So anyways, back to Sci-Fi Fish. All right. Congratulations. Your hypothesis is now considered a theory. It's declared a theory to explain the observation. Now, this is very, very, very important. Just because it's a theory doesn't mean it's a fact or it's true or any of that. Every single theory is challengeable, is disprovable. It's open for debate. It's open for discussion. A theory can never, ever, ever be a fact. And a theory can never, ever, ever be a scientific law. You have to remember that. It's very, very important. All theories are falsifiable. That means all theories are challengeable. All theories are open to being refuted and challenged. Okay, and a great quote, I think that can help you to remember this, is Albert Einstein. This was attributed to him. He said concerning his theory of relativity, no amount of experimentation can ever prove me right. Can never prove you true. Can never make you a fact. And then he went on, a single experiment, however, can prove me wrong. Right? So anybody can come up with a new test to test one of those other hypotheses, that maybe a UFO or something else is responsible, and maybe they can show that that's actually more of a probability. They test and show that you filling up your gas tank actually had nothing to do with it. The UFO was just shutting on and off every hour. Every hour it was shutting on and off and just happened to coincide with your gas being filled up, and there was a leak in your tank and it was spilling out. So it had nothing to do with gas. It had to do with the UFO, right? So every theory can be proven wrong. It's open for debate. Okay. So we've just walked through the scientific method. That's what it is. It's a pathway to understanding, to trying to come to a understanding about something in a very logical, stepwise methodology, function. And we'll look in a future episode, we'll be looking at why the scientific community falls foul of this all the time. But for now, I want to move on to another discussion to explain, because we've just mentioned fact here, that a theory can never become a fact, and a theory can never become a scientific law. And I want to look at what those differences are, so that you can also have a better understanding for what a fact is. So when a scientist says, this is a fact, are they really talking about a fact? Is it really a fact according to science? Or are they not talking about facts? And maybe also scientific laws. What are those? All right. So let's move on. What's the difference between a scientific theory, which we've just looked at, what a theory is, a scientific law, and a scientific fact? Okay, well, we looked at what theories were. So what's a scientific law? Well, scientific law relates to an observation, all right? So, for instance, the scientific law of gravity states that one piece of matter is attracted by an invisible force to another piece of matter, that force changes in strength with the size of that matter. That's really a simplistic definition of gravity, the law of gravity. But that's not explaining what is causing the force or what causes gravity or the question of why. It doesn't answer that. Laws don't answer why. It's just more the observation. Now, two pieces of matter, throughout all human history, we've seen this. When you drop something on the ground, it falls. It's attracted. One piece of matter is attracted to another piece of matter. Okay, so that's a law. It's just an example of a law. And we can get into more detail on that later. Okay, what's a scientific fact? What is a fact according to science? Well, a fact is something, this one's a little more challenging, so we need to, look at this carefully. A scientific fact is something that is empirically true. It's been tested. Anyone in the whole world can measure this and look at it. It sounds a little bit like a theory, but it's not. So, it's empirically true in the sense that to the best of our knowledge it is so. For example, a fact would be the airline company Boeing builds its 747s with a wingspan of 196 feet. That's a fact. You can measure that. That's how they build it. That's how they make these planes. It's 196 feet long. You can go and take a tape measure and measure that. All right? And see that. That's a fact. A theory, in contrast, would be the Boeing 747 can't fly faster than 614 miles per hour. Okay, the first thing was a self-evident statement, observed and directly measured. The second statement would have to start out as a hypothesis that would have to be tested a whole bunch of times, right? They'd have to fly the 747 over and over and over and over to try to corroborate that statement until it became a theory. But here's the thing. Maybe a different pilot or a different fuel in the engines or just some fluke or whatever could prove it wrong. The Boeing 747 could all of a sudden, oh my goodness, it's doing 615 miles per hour. Well, that just proved the theory wrong, right? But no matter what, a Boeing's wingspan, a 747 airplane's wingspan always is 196 feet long, all right? So they're very different things. So let's look at another example. A fact would be quartz crystals are made up of a certain number of silicon and oxygen atoms. All right? This is by measurement and by definition. It's what quartz is. It's empirically tested. It's shown. That's our definition of what quartz is. Okay? A theory would be quartz crystals form when silicon and oxygen atoms come under pressure and maybe temperature. Okay? Well, that's different. That's getting at the why. Why does quartz exist, right? So this would form as a hypothesis. And a whole bunch of silicon and oxygen atoms would have to be put together in a press in a lab somewhere, and they'd be put under intense pressure and heat maybe until they form quartz crystal. Maybe you do this like 1,000 times and you always end up with quartz crystals. So maybe you get to a theory. But there may be other ways to make quartz crystals without pressure and temperature that you don't know about that could prove your theory wrong. So they're very different. Okay, all quartz crystals are made up of silicon and oxygen atoms, a certain number. All right, but we don't know if all quartz crystals are made from temperature and pressure, right? So that's a difference. All right, one more. We'll go through one more because this one's a little harder and I want to use some examples to get to it. All right, a fact. Today, the air temperature at my research station in Death Valley was 120 degrees Fahrenheit. That's a fact. You measured that on a thermometer, all right? 120 degrees Fahrenheit. It was measured, all right? Here's a theory. Death Valley is the hottest place on the planet. Okay, do you see the difference between those two? What's the difference? One is a direct observation and measurement in a controlled environment, and the other is a hypothesis that has to be tested by taking temperatures in all kinds of places all around the world. But there's always the possibility and actual truth that you missed this spot or that spot because you can't measure everywhere, right? And you missed a place that's actually hotter. You just didn't visit it and you haven't found it yet. Okay, so that's the difference. So I hope this is an introduction to the scientific method, theories, laws, facts. I hope this helps you understand it better. So in our next episode, we'll have an introduction to the scientific fallacies that the scientific community has perpetuated as science upon the world. So until next time, this is Sci-Fi Fish, logging out.